In this video, we're going to work through a incline ramp pulley problem. We have two blocks M1 and M2. They're connected by a light string as shown below. These blocks are further connected to a block of mass M by another light string that passes over a pulley of negligible mass and friction. Blocks 1 and 2 move with a constant velocity v down the inclined plane, which makes an angle theta with the horizontal. The kinetic frictional force on block 1 is F, and that on block 2 is 2F. On the figure below, draw and label all the forces on block M1. Okay, so I'm going to start with gravitational force, and that's going to be Fg, or I'm going to write M1g. So that's the gravitational force on the block. There's also a normal force from the surface, 90 degrees to the surface. Okay, and there's friction. This is going downward. The velocity is going downward this way. And so I know the friction is going to be up. There's also a string. So there's two forces there. So I'm going to have a tension force this way. I'll call this T1. And then there's also a friction going this way. And we'll label that F because it says that the friction force is going to be F between the box and block and the surface. Okay, so that is my force diagram. I'm not going to break anything into components. If they ask for force diagram, just draw those forces. Don't break anything up into components. For part B, determine the coefficient of kinetic friction between the inclined plane and block 1. Okay, so now in this problem, now I am going to break into components, and I'm actually going to draw on the picture right here. So once again, I have M1G, and this is, and normal is going to be over here, normal, okay. And to figure out the coefficient kinetic friction, the equation is mu times n. So I'm going to need to know what n is equal to. And yes, there is a tension force here, and there's a friction force there, and I'm going to break this into components. I'm going to use a different color here. So you have the perpendicular component to this ramp, and then you have the parallel component. This is theta, and this is also going to be theta. Because this is the opposite, the side of theta, this will be M1g sine theta. But what we really want is this one, which is going to be M1g cosine theta. Okay, so this normal force is going to equal M1g cosine theta because it's not accelerating in that direction. So I know those are balanced forces. So I'm going to substitute that for the n. So now I have, so F is equal to the coefficient of friction, and now I'm going to substitute the M1g cosine theta. M1g cosine theta. I'm going to solve for mu, and mu is going to be the friction divided by M1g cosine theta. And I'm just going to box in my answer. It's going to be right there. Okay, so moving on to part C. Okay, in part C it says to determine the value of the suspended mass M that allows blocks 1 and 2 to move with constant velocity down the plane. So I'm going to first draw a force diagram for each of these blocks. All right, so I'll start with block 1. And block 1, there is the gravitational force, M1g. We have the normal force, call this N1. And we have two forces in this direction up the ramp. This is going to be T1 as well as the friction. And I'm going to also break this down into components. So this has two components, horizontal and the parallel and the perpendicular component, and that's theta. So we're going to need this parallel component, which is going to be M1g sine theta. Okay, and then moving on to block 2. This also has a normal force from the ramp. We have T1, and these two are action-reaction forces. There's also T2, and also friction. And I'm not drawing these to scale, but it's in the right direction. And this is going to be M2g. And then I can break that into components as well. And if this is theta, this will be m2g sine theta. Okay. And then lastly, I have for block big M, there's two forces there, T2, and this is action-reaction force with that one, and this has a weight of mg. Okay, so now I want to combine these. We're going to write a F equals ma Newton's second law equation for each of these, and then I'm going to combine them. So starting with the first one, because I know it's moving at constant speed, we know the forces are balanced, so the forces go in the positive direction. So I'm going to make this positive. So this is my positive direction, okay, down the ramp this way. So all the forces going down the ramp minus all the forces going up the ramp. So m1g sine theta minus T1 minus F is equal to 0. Okay. The second block, we have T1 plus m2g sine theta minus T2 minus 2F equals 0. Okay. So those are all the forces down the ramp minus all the forces going up the ramp. And then finally, our block big M, we have T because the pulley redirects the direction. So I'm taking all the forces going up, T2 minus all the forces going down, mg, and set that equal to 0. All right, so now I'm going to hopefully find some forces that are canceled out. So the T1s cancel out. That's good. The T2s cancel out. That's good. Okay. And then here's what we have left. So we have m1g sine theta, let's see here, plus m2g sine theta minus mg minus, and then there's the negative f and the negative 2f, so we have negative 3f is equal to 0. And we're looking for what m is, so I'm going to move the m to the right, and then I'm just going to combine the g sine theta, so we got m1 plus m2, and I'm going to factor out the g sine theta, and then on the right, and then we have minus 3f is equal to mg. Right. And the last thing we need to do is just divide g on both sides, and I'm going to flip the left and the right hand side. So we end up with m is equal to m1 plus m2 sine theta minus 3f divided by g. All right, now we're going to go to part D. And part D is the string between blocks 1 and 2, that's this area right there, is now cut. Determine the acceleration of block 1 while it is on the inclined plane. Okay, so block 1, the forces now, there's no T, so this forces now is just going to be m1g, and we have n1, and we still have some friction, and we can break this into components, theta. So this component here is m1g sine theta, right? So using Newton's second law, net force equals ma. All the forces down the ramp, we're going to make this positive, is going to be m1g sine theta minus all the forces going up the ramp, which is friction, is equal to, the math is my system, m1a, and m1 is my system. Now we're going to look for the acceleration. So the acceleration is going to be, I'm going to divide m1 on both sides and flip left and right. So I'm going to end up with g sine theta minus friction over m1.